Good evening, everyone. Welcome back to another live stream as part of Exercism's Analytical April, where we'll be reviewing and going over exercises and other things related to analytical languages. So, for my part, I'm going to be working on the Julia language and doing some exercises in the Julia language, talking about Julia and things we have to think about when working with Julia, and some of why things are the way they are. Won't try and get into too many of those details. So my name is Aaron. I'm a developer based in Boston. So it's about 7 p.m. for me here. Wherever you are, thanks for joining me tonight. And just give me a second while I get set up. All right, so I'm just going to go ahead and share my whole screen here just for the sake of easiness. I have on my left-hand side here, I have my VS Code window. On the right-hand side, I have my terminal. So I will be, this is the way I usually like to work. We can access Julia from within VS Code. I usually like to use the external terminal, mostly just because it's what I'm used to, and also because it makes it easier to run things and then detach from them and that kind of thing. So tonight I'll be starting with the rational numbers exercise. So that is, marked as one of the harder exercises, although it's not too bad. And the reason why I chose it for tonight is just because it's mathematically oriented, and gives us a chance to show off some of the neat features that Julia offers, as far as especially mathematically oriented things go. So I should already have the exercise here. But what I'm going to do tonight, at least for this part, is I'm going to demo a little bit about how we usually work with packages in Julia, just because the exercism exercises are structured slightly differently. It's not all that much different, but just so those of you who aren't familiar with Julia can get a taste of how we would start from scratch with our own package. It's very, very simple. It will take no more than a couple of minutes, but I think it's something that's neat to go over. So you'll see here that I've started my Julia window, right? I started my Julia REPL, I should say. And I'll make this just a little bit bigger for now. And the first thing I'm going to do is press the right square bracket, and that brings me to this package manager window. And then what I'm going to do from here is I'm going to type generate and the name of my package. And if I look in this directory, now I have this rational numbers.jl. And I've just called it that because it's typical with Julia packages to add this .jl prefix to indicate that it's a Julia package, kind of like how with Python you'll see like pi prefix, or with C++ you sometimes see, C++ prefix or suffix on a package. The actual module names themselves usually don't include this, or pretty much always don't include this, but it is a typical part of the package name. And you'll notice that if I go into this directory now, oops, rational numbers, I really haven't got much. I've got this project.toml, which is where Julia keeps track of my dependencies, which for the purposes of this exercise will be basically nil. And I've got this source directory where, I'm going to be writing my code. Now, there's one other thing to mention here that I'll probably want to do for any other package, or for any package that I actually do work on, and that's going to be tests, right? And that's actually how Exercism judges how we're doing these exercises, right? Is they have a test file that they set up, and we have to satisfy all those tests in order to pass the exercise, right? So the first thing I'm going to do there is make a test directory. Right now there's nothing in it, but what I'm going to do is I'm going to take the test file from the exercise, which has the typical name that we give a test, if there's only one test file, or the top level test file in Julia. It's run test.jl. I put that in my test directory. And the reason why I'm going to do that is because now if I start my Julia REPL and either do Julia ---- project or activate within the REPL, either one of those is good if I were to type activate like this. I've already activated this package, but I could do that as well. And if I type test, it's going to run that test file. And the first thing it does is it complains that I haven't actually added this test package. And why is that? Well, let's go ahead and open up this rational numbers package. Right now, there's nothing in it, or there should be nothing in it. And if I look at what Julia has actually generated for me, right, they've given me a module. They've given me a nice little hello world message, and that's just about it. And this is the place where we start Julia packages. If I look at this run tests file, well, there's a whole bunch of stuff in here. The one change I'm going to make right off the bat is instead of including this, and I'll make this a little bit bigger. You can already kind of see this is a little tiny. Move this over so we got some more room for our text. The only change I'm going to make right here is instead of this include rational numbers, I'm going to write using rational numbers. And what this is going to do is this is going to, make this file aware of this rational numbers module we're going to be working in. Include rational numbers would just include the whole contents of this rational numbers file, which, like I said, this is how we usually do the exercism exercises. But for tonight's purposes, I just kind of wanted to demo a more traditional Julia package workflow, just for those of you that might be interested in that kind of thing. And the first thing I'm going to do after that is disable all of these tests, except for the very first one. Right, I'm going to take a test-driven approach here. Well, the first requirement, right, is that rational number is a subtype of real, right? This is a symbol that, as far as I know, this exact symbol is more or less unique to Julia, but this idea isn't, and I think other languages use a single less than symbol to make this distinction. And this just means that we want our rational number type to be a subtype of real, right? And if I go ahead and add in this test package, which I need, right, because I'm going to be using this here, and type test again, well, the first thing it complains about is that I haven't even defined what a rational number is, which is going to be a problem as far as implementing rational numbers, right? So that's the first thing we'll do. We'll look at this module and say, okay, well, I don't really want this greeter function. The only thing I know for a fact that I need right now is a type called rational numbers, or rational number, sorry. And this is pretty common, right? If we have a single type that's kind of the cornerstone type of a package, we'll call the package, the plural version and the type the singular version. So we've got this package rational numbers, or this module rational numbers, in which we've got this single type rational number. And of course, in real life, we probably wouldn't have such a simple structure, but usually we have one module or only a few modules per package, and base names on that kind of thing. So defining the type will get me part of the way, right? Except there is one thing I'll still have to do here for my package, and I actually have to export this name. And why is that? Well, since in my test file, I've just done using rational numbers, unless I export this symbol from the rational numbers module, this test file will have no way of knowing that it exists, right? So I export rational number, I run my test file again, and now I get a different error, right? I get the error that rational number isn't real, right? It evaluated this expression, and this expression failed. So now I can see this rational number type, but it doesn't satisfy the properties that our tests have laid out, which are pretty sensible, right? We want a rational number to be real. We don't want it to be an integer, right? It's not a subtype of integers, because rational numbers and integers are not the same thing. We'll see, they're very closely related, but they're not the same thing. We don't want it to be a complex number, at least not at our first go, right? So it makes sense to restrict to a real number. And that's all we really need so far if we're going to take a strictly test-driven approach. If I were to fill this in, that first test passed. And one of the nice things about working in a module like I am right now is we don't have to constantly keep refreshing and restarting the Julia prompt, the Julia REPL, whenever I change the definition of a type or some kind of other constant, right? Because it's wrapped up within this module. And as long as I have things set up right as far as Julia goes, we can change these constants, these type names, these are type definitions and that kind of thing without having to restart our REPL session. And the way we do that is via this revise package. So I've already added this in the background, and this is something that usually is added to your top level Julia environment. And this package just kind of keeps track of what you're working on and monitors changes. And whenever you change things that are quote unquote constant, It will, replace things in the background so you don't have to start your instance over again. So this is something I'm not going to talk about too much. Suffice it to say, when you install Julia, the first thing you should do is add revise. Okay, so I mean, as you might imagine, this is really not going to get us very far other than passing this first test, right? And as far as the next test, right, this introduces a new keyword that we didn't see in my last stream that is pretty common. And this is an idea that pops up in other languages, other test frameworks as well, right? Where we're not testing so much what the value of this expression is, because I mean it doesn't really make sense for it to have a value in the first place, because we want it to throw some kind of error. And we want it to throw a particular kind of error as well. Okay, so in this case, we want to throw an argument error whenever we specify a rational number that's 2 zeros. Okay, specifically, we're concerned about, or I guess more generally speaking, we're concerned about the denominator being 0. But, if we're being strict about what's laid out here, this is what we're going to want to watch out for. Okay. So how do we deal with this? Right. This is a check we basically want to do when we construct the rational number. And so, I mean, as you might imagine, we're going to have to define or modify a constructor in order to get this to work. So what have we got so far, right? If I just write tests, okay, all that I've got is that a method error, but not an argument error. Okay, what's that about? Well, if I basically try and do what I'm looking to do here in this test file, right? If I do using rational numbers, so I can bring the rational number stuff into my namespace, and then write rational number, say 1, 1. Well, it's mad because there's no rational number constructor that looks like this. And for those of you paying attention to what we've implemented so far, there's actually no rational constructor of any kind, right? Because Julia does provide default constructors when I do specify fields, right? When I do specify, what might be called member variables in another language. But I haven't done anything because my tests haven't yet required it. But of course, the natural thing I'd have here is I'd have a numerator and a denominator. Now, last time I left it like this and continued on and, circled back to the point that, usually we don't want to do stuff like this in Julia. And what do I mean by stuff like this? Well, even though I haven't written anything here, this X and Y are really of type any. And what that means, basically, is that in order to act on, to reason with these values, Julia has to store them behind a pointer because it has no idea what kind of type is in there. So this is basically Julia acting fully dynamic, right? In that it has no knowledge of the internal types of this structure, at least outside of the constructor, right? Because if I set things up like this and I write rational number 1, 1, oops, using rational numbers, right, this will work, right? And if I look at the code that this emits and everything in assembly, which I'm not going to get into, right? I would see that at least in the case of the constructor, I can have some information about these types, right? Because it has to know, where to save them and stuff like that. But as soon as I start doing any kind of other operations on this type or passing it to another function or anything like that, I'm going to run into trouble, at least as far as performance goes. So what we can do to save ourselves the hassle is to add a type parameter here. So I add the type parameter to the type itself, kind of like this. So this is a lot like what we do in C++, right? In C++, I might have something like, template type name T rational number, right? It's a similar idea, right? In that I'm parameterizing this type. And I'm also requiring that the numerator and the denominator have the same type. Oh, hi there. Nice to see you. So I'm also requiring that this numerator and denominator have the same type, which, strictly speaking, isn't 100% necessary. But, whenever we're acting on the numerator and the denominator, and we're doing operations with these rational numbers. If we have these be different types, we're going to end up converting back and forth and promoting all over the place, even more than we would need to otherwise. So it makes sense to keep these the same. Right? And if we think about the mathematical concept of a rational number, we're thinking about the ratio of two integers, right? And if we're talking about the size of those integers or their signedness or something like that, those really should be the same, at least in concept. And then, strictly speaking, be the kind of thing that you would wait to do until you had a good reason to, right? So we've got this type, rational number, right? And I can make one restriction here that I don't strictly need to, but it is good to build in information. And I can say, well, I want this to be parameterized by an integer. Okay, so this means that whenever I try to construct a rational number t, I can only do it out of two values that are integers. And an integer here, right? This is as my helpful tooltips say, this is this abstract supertype for all integers, right? So it'll add, so Julia has, of course, the regular, like 8-bit integer and stuff like that. 16-bit, unsigned 8-bit, all that good stuff, right? Any of these will work. And then the regular int, is an alias for 64-bit integer. So Julia handles this stuff pretty nice, right? Because it's all very explicit. We don't have to worry about unsigned short and stuff like that, right? And if we want to work with just a regular integer, we can do that, at the full word size. And if for some reason I want to do an int 32, of course, I can do that. So this is very similar to the setup that we have in C or C++ or one of those languages, except I think the names are a little bit easier to work with. Of course, C++ has your standard, uint 8t and that kind of stuff, but that's not quite an afterthought, but close. Whereas this is an integral part of the language. These are things that can be the types themselves can be manipulated as data, kind of thing. So that's one of the things about Julia that seems at the surface kind of traditional, but already I can do stuff like promote type of an int 32 and an int 16, and it'll I can work with these types directly. I can do operations on these types and that kind of stuff. So it's kind of like what C++ has as far as concepts go, right? I forgot the word from last time. Someone introduced me to that concept, if you'll pardon me, last time. And that's basically how this works, right? And in the chat, I've got a question here or a comment. I believe on 32-bit systems, int is 32 bits. As far as I know, right, if we talk about the standard compilers, the standard implementations, even in the case of, say, like C++, right, when you write just int, this is, in 32t, 32-bit integer. You can get a 64-bit if you want, but as far as I know, by default, these are going to be 32-bit. Whereas in Julia, we always start with 64. And of course, in most cases, that's not going to matter that much, right? But that's the way it works. And of course, you're right that if on a 32-bit system, you really only have, or at least natively, the 32 bits in the first place. So if we were to be working in Julia in 32-bit, it makes sense for this int to be 32 bits instead, which is one of the reasons why it's set up like this. Kind of like in C++ or C, where int can change based on the architecture and all that stuff. Same thing with this capital I int. I also like that the type names are always capitalized. I'm constantly screwing myself up in C++ and Python by forgetting, that int and string and all them are lowercase, and basically every other class isn't. That always screws me up. So back to the matter at hand here. So there's one thing to mention, right? Even though I've just written this definition, and I'll, write using again here. Even though I've just written this definition, and it looks a lot like kind of a weird cross between a C++ structure and, regular C structure kind of thing, right? And if it wasn't for this bracket stuff, it would look kind of like a C struct, right? But the interesting thing is, and the thing to note here, is that I have this rational number constructor, if I can spell it right, that it gives me for free. So basically, it's as if I wrote, down here, function rational number. I have two inputs, which I'll call n for numerator and d for denominator. And if I'm careful, right, well, one thing to watch out for, to illustrate my point, right? If I try and do rational number, say 1 and, or let's do like this, int 8, 1, and int 16, 1. I believe this will break. Right. So here's one thing to illustrate right away. I do have a constructor for free where both types are the same, but not where they're different. And that makes sense because the way I've laid out these types, at least as far as the internal representation goes, these have to be the same. So we'll always basically get kind of the most natural constructor of just, listing the elements or listing the fields in order as long as they're the correct types, and then, constructing accordingly. So basically this would look like this. And because I've set up there my t should be an integer, subtype of integer, right? I can put that requirement here. Of course, equivalently would be put in the code as well. And then I'd have, return rational number n comma d. And you might notice, or one thing you might know if you've worked with Julia at all is I don't really strictly need this return statement here. Julia automatically returns the, whatever the last line returns. I always put the return statement, always, always, always. Even if it's a one-line function, even if it's returning nothing, right? I just really like to make it clear what I'm doing at a given time, even just for myself. So we basically get this form of this constructor for free. But if we want to have different types, we're going to have to deal with that separately, right? But you might ask, if I were to define this constructor out here, I could totally do that, right? But what happens if I want to make modifications or introduce behavior or invariance or checks or whatever on that, automatically generated constructor? I might want to do that, right? That's something we do very commonly in object-oriented languages. And Julia has a notion of this, right? And that notion kind of works like this. Basically, this quote-unquote, auto-generated constructor is the constructor that always ends up getting called, right? All my other constructors will end up, delegating to that one eventually, at least, in principle. So it's special, right? It's kind of intrinsically associated with the type. So within Julia, we call this an inner constructor. And so what we do is if I define my constructor inside the type definition instead, which is the only time we would do something like this in Julia, and I do the same thing, right? Num t, denominator t, and actually just for the sake of clarity, I'll call this n and d, where t is an integer. Right. So what this is doing is saying, this is signaling to Julia, hey, this automatically generated constructor, I want to do something special here. Okay. I want to introduce something. And what do I want to introduce? Well, as far as a rational number goes, the one thing I can never have is a denominator of 0. And if I look at my requirement here, I want that to throw an argument error. Strictly speaking, I really, the test only requires it to throw an argument error if they're both 0. But I can have 0 in the numerator just fine. It's really only when I have 0 in the denominator that I have a problem. So I'm going to, use my judgment there and go ahead and code for what I kind of know this wants to look like. So how do I check that? Well, simple approach first is just an if statement, right? There might be better ways to do this that, we would think of if we really wanted to optimize, but let's leave that for another time. So if my denominator is equal to what? Well, I don't want to just write 0, right? This probably will work, might not. Julia is actually a little bit more strict with this kind of thing than a language like C++. And what I mean by that is, if I were to write this in C++, as long as there's some kind of implicit conversion from D to, 0 as the regular integer, that would be fine. But Julia doesn't really do implicit conversions, at least not as a general rule. So either there has to be, an explicit conversion defined somewhere or another. So what I really want to do here is something like this, is 0 of type t. And so what the compiler will do is it will see this and we'll just replace this with the appropriate value of 0 for each value of this typed parameter t, right? So every time Julia sees a new value of this type parameter, at runtime or at compile time, or usually most often at runtime, it will generate a new version, a new method of this function with a different value for 0 here, according to what that type should be. Okay, and that's what the secret sauce, the key ingredient of Julia, right, is that just-in-time compilation. In that when we parse the file, we do kind of what's similar to we set up these functions, we define the functions, and then as soon as we run the function the first time with a particular set of values of a particular set of types, right, Julia will compile a version of that function, at least as far as it can, for that type. And then it sees another type, it'll compile another version, right, and it caches these as we go, so we only have to pay that cost the first time we see it, right? And when I say as far as it can, that's kind of what I was referring to when we had our original constructor, right? That looked like where these t's were replaced with any's. The compiler couldn't do all that much about that, right? It's going to say, okay, well, if I'm going to pass this to anyone, I don't have any knowledge about what the internals are, what instructions to generate, that kind of thing. All of that has to be done at runtime, right? It has to say at runtime, what type is this? What do I do, right? So Julia can, the way I like to think about it is Julia is a compiled language that can fall back on being a dynamic language. Is a good way to think about it. If you're trying to write idiomatic Julia that performs well, that's structured well, that behaves well with Julia's type system, it's usually best to think about it more as a compiled language. It's just the way it compiles things is a little bit strange because it, the compilation happens, just ahead of time. Now, one thing that's really, really cool is that with the latest version, or not even quite the latest version, the upcoming version of Julia 1.9, there have been some massive improvements as far as caching those compilation results from run to run, from session to session. Before, it basically had to be done for each session. So if you've used Julia before, one thing you might notice is things like plots take forever the first time, right? Because plots are a very, very, very type-specific operation where there's a lot of different types going on. There's a lot of different inferencing that has to go on. Whereas, now with the upcoming 1.9, that kind of thing will be ameliorated quite a bit. And I've noticed a difference in even my day-to-day work with, numerically intensive code that used to require a lot of pre-compilation time. Now from session to session tends to work a little bit better. And that all depends on making sure we're careful about how we invoke this kind of stuff. So you see a lot of type parameters in function or in type definitions, right? In struct definitions, if you want to use the syntax name. But a lot of times in functions, we should try and avoid using them because the compiler will be able to figure out the rest as long as the types are set up right. And I'll talk about that as we get to that. So if D is 0, what's the error we want to throw? We want to throw an argument error. And I'll just say divide by 0. Oh, hello there from Paris, huh? Welcome. And of course, we don't have to import any of this. This is just something, there aren't that many error types, so Julia just has them all part of base. I have this optional message that I could probably just drop, but I might as well include it here, right? And if I try and run this, oops, keep skipping the E. So far, so good, right? This second test passes as well. It throws an error of the appropriate type. And, strictly speaking, test-driven development, that I'm done so far, right? But I'm going to go ahead and say, okay, well, at least at this point, I'm sure I'll have to think about this a little bit more, but at least at this point, what I'll write is return rational number and comma D. But there's actually one problem with this, right? The compiler actually won't know what this is because I'm currently defining what, like I said, the last stop constructor really is, right? What everything ends up ultimately delegating to. So this is the one case where I use this very special construction operation in Julia called new. And I'll write new brace T. This operator is only available inside a inner constructor. It has no meaning outside of this inner constructor. And this is, a little bit reminiscent of C++ syntax. right? Because we're saying, okay, well, this object, we're going to, instantiate, allocate, whatever you want to call it, a new one with the type parameter t, right? It has just this single type parameter constructed from these two values, right? So strictly speaking, we always get this for free. This is what the compiler always generates. It just isn't written there. But if you want to think about this in the most concrete terms, you can think about whenever I write a structure definition, I always get, at least this. And then if I want to add special behavior within any constructor, right, or should I say within all constructors, right, whenever I construct a rational number, I want to check some stuff. Then I add this inner constructor in here. So this is not something we should do unless we have a good reason to, right? Most of the time, our type definition should just look like this. But for our purposes, right, we do know some stuff that we want all rational numbers to be able to satisfy without, before we can even construct them. And like I said, this last line, there are some probably extra concerns we'll have here, but I'll just leave it like this for now. And we'll address those as we come to them. Okay. So far, so good. Like I said, now we're moving on to this next test set, right? So we've got two tests here. Tests of these built-in operations of 0 and 1, these built-in functions, right? We've already used one of these for an integer type. So basically, we want to set up what these mean for our new type, our new number type. And it's the sensible stuff, right? Or at least, a version of the sensible stuff, right? The 0 one is a little bit ambiguous, so we make a decision, rational numbers we represent it as effectively 0 over 1, right? 0 over 2, 0 over 1, 0 over 3, right? All those are, if we're strictly thinking about it, in terms of converting back to integers, all of those are equivalent. This is the way we're representing 0 just for our purposes here. And if we think about ultimately, if we reduce our rational numbers, they should all end up looking like this at the end of the day, right? 0 over 2, 0 over 3, they're all just going to get reduced down here. 1, right? What, the return value of this 1 function is, that makes a little bit more sense, right? 1 over 1. Again, at the end of the day, if we reduce everything down, we'll just get 1 over 1. So how am I going to define these? More or less exactly as I see them, right? Where I'll say, okay, well, I have this function that I want to define. If I look and be careful, right? Base and 1 and 0 are part of this base module. So if I'm going to write a new method for those, I have to qualify them, prefix them with the module name. Right, this happens in Julia whenever we want to add a function to an existing module, which is totally fine and actually, a regular part of the language because of the, we're not object-oriented in Julia. I have to prefix it with the module name. So since I'm overriding a module or a function in base, I don't actually need this quite yet, I prefix it with base. And I want to do, first I'll do the 0 function. What do I want this to look like? Well, I'll have a rational number. I'll just call it R. And the 0, right? 0 is going to return rational number. Well, there's a couple of different ways I could do this, right? I want to have, at the end of the day, 0 over 1. And if I want to keep type aware, right? If I want to keep what's called in Julia type stable, I could write it like this, 0 R over 1 R. So type stability is, of course, again, not something that is unique to Julia, but is a pretty big concern. And that's basically that, the requirement that the compiler can, know what the given type of a given variable is at any given time and that type doesn't change. Otherwise, we have to fall back on this any or business, right? Or effectively, if we want to think about the nitty-gritty details, then Julia has to do stuff like store the value in a pointer to the base type and delegate and do all that stuff, which has runtime cost. So this will say, whatever type rational number is, whatever this type parameter is, I will sort out the appropriate 0R, 1R. But of course, the problem here is that, 0R and 1R aren't defined. So what I'll have to do is extract my numerator and denominator. Right? So I'd want to do something like this, 0 num, 1 num. And I could do this, right? I could write it like, r.num, 1 r.num. But there are a couple of reasons why I personally would not like to implement this way. One, while it is true that the numerator and denominator should be of the same type, I mean that's an assumption that I can make that I don't necessarily want to have to remember all the time. Right? It's like mental overhead. And the other thing is here, like why the numerator and not the denominator? This doesn't really depend on the actual values of the numerator denominator. It just depends on their types, right? So there's a better way to do this, and that's to use the type parameter. So I always have to write this when I use a type parameter. This is equivalent to writing t as a subtype of any, right? Any type we want. But I already know that t should be an integer. And then again, strictly speaking, I couldn't construct this R in the first place if t wasn't a subtype of integer, because I've required that within my struct definition. But I might as well write it here too to make it clear, at least for readability's sake. And then what I can do is just replace these with the much more sensible 0t, 1t. And we might have also noticed, right? My editor here has signaled to me that this variable is used or included but never used. And that's because, as I alluded to before, right, we don't really care about the value of this R, just its type. So what I can do here is write this like this. And this function definition says, well, okay, I don't care what the value you pass me is. All I care is that it's a rational number, with parameter t. Anytime you pass me one of those, as long as, depending on what the value of t is, I could fill in the same result. And as far as 1 goes, right, we can do basically the same thing, except with 1 instead. And if I check where I'm at here, okay, right? So we might have noticed some problems already. And that's basically, right, that we have some issues with, how we are setting up these types in the first place. So let's think about what we're missing here, right? This is basically saying that Julia is trying to do some conversion operations that it's not too sure about. It's trying to fill in some details, and it's struggling, right? Because we haven't told it how to actually, it's basically trying to convert everything to integers. It's trying to compare these, field by field. It's getting confused here. So what we really want to do here is make sure that we can deal with rational numbers, right? More generally, or when I say more generally, what I really mean is, that we can kind of construct any rational number we want here. So I'll add this other constructor, and I'll write, I'll use the same kind of notation. But now I'm going to look at what happens when we have two different types. I'm going to call it Tn and Td. I will go ahead and encode here that these are going to be, right, of subtypes of integer. Again, not, in this case, it is strictly necessary, right, because I only want this to work in the case of these both being integer types. And how am I going to deal with this? Well, in Julia, we have this idea of type promotion, right? And what this says is, okay, well, if I have two different types, if there's some kind of relationship between those types, right, there might be some kind of common type I can convert them both to in a sensible way. And not only that, the type system itself, as long as we define the right methods and things, can handle a lot of the legwork for us, as long as we define the right rules, the right relationships. So in the case of integers, these are all already defined, right? I actually used one of the operations before when I wrote promote type int 16 or something. I don't think I wrote exactly this, but something like this, int 8, right? This is saying, okay, well, what is a common type between int 8, 8-bit integer, 16-bit integer, that they can both be converted to? It can represent both, right? And that's int 16, right? Just, widen this out to 16 bits, leave the other one alone. And so for our rational numbers, we'll do something similar. We'll say, okay, well, at the end of the day, if we get two different types for our numerator and denominator, we'll just convert them to a common type. We'll say, okay, well, whatever the promotion of Tn and Td is, well, we'll convert, right? We'll say we'll return rational number. And actually, no, I'll be a little bit verbose, right? All right, nt is convert Tn. dt is convert Td. And then we'll return rational number nt dt. Right, and this is falling back on, right, ultimately, this default constructor. And so let's see what we've got now. Oops. Okay. Oh, of course. There's an even simpler problem here that I just totally glossed over in my eagerness to explain all this stuff. What's happening here is we actually haven't defined what this operation means, what this equals equals means, right? This is a common problem or a common thing we do in other languages as well. But as you can see, Julia is trying to fill in the gaps here. It's trying to say, okay, well, you've got equals equals. Maybe I could convert them to rational. I don't really know what's going to happen here, right? So what I'll do is say, okay, well, we'll define this equals operation the way we want to, the way that's sensible. Base dot is equal. I could also write it like this, use the symbol equals equals, but I prefer to, use the function names if I can get away with it, just because the symbols are a little bit strange to me. And I'll just say, okay, well, I've got two rational numbers. I'll call them x and y. And what does it mean to compare these two? Well, they're equal if their numerator and denominator are equal, right? That's how fractions work. We compare the numerators, we compare the denominators, we check if they're equal. Okay, so I could do stuff like this. I could do something like, return x dot denominator is equal to y dot denominator, y dot numerator is equal to x dot numerator, right? And of course, the order's not exactly consistent here, but that doesn't really matter. That's fine. But, a lot of the times we in Julia like to think about members, about fields, they're called in Julia, about these variables being private unless kind of otherwise specified. So if I start using those values quite a lot, we usually like to define functions, effectively getter functions to access them, an interface instead. That's not a strict rule, right? If you have a class that's really just plain data that you want to reach into and change stuff a lot, that's fine. But the reason why this is also popular is because you might notice something a little bit strange here if I write, using rational numbers, take x is rational number 0, 0. Oops, and of course, broke my own rules here. And I can do x dot denominator, but what happens when I do x dot denominator equals 2? Right. Structs in Julia are immutable by default. I could write this as, mutable struct, but this is something you should really never do unless you have a very good reason to, because this will automatically put you in the performance killer territory I talked about before, because Julia will kind of automatically have to store these values in the struct behind layers of indirection to deal with the fact that they could change either in type or in value. The one caveat to that is if I were to have a field that was of a type like a vector or something like that, I can change the values in the vector, right? Julia will let you do that kind of stuff because that's not strictly changing, the underlying, they draw a distinction between changing a value of something like an integer, like a primitive type, versus a, collection, a composite type. That's something to keep in mind because I don't find that the most intuitive behavior, but you get used to it after a while. And so what I'm going to do here, just to be idiomatic, is define two functions, right? Numerator for rational number. I'm going to return just the numerator. Oops. I might actually want to return the numerator, right? Denominator for a rational number. Okay. And actually, I will do that down here. Where I'll say, well, we'll check first if the numerator of x is equal to the numerator of y. And then we'll check, reversing what I did here just because it's easier to think about it this way, right? Denominator of x is equal to the denominator of y. And there's a couple of things to note here, right? We'll automatically know, the compiler will automatically know which value, or which method of this equals of this is equal function to call here, because it will know what type this x and y are. Even though, right, the key difference here with how types work in Julia, or function definitions work in Julia versus C++ templates, is that I don't need to always include the type parameter here in order to make this parametric, right? This is equivalent to writing basically something like this, tx, ty, where tx, ty. This is the same thing. And I could totally write it this way. And I honestly used to do this stuff quite a lot before I really got the hang of this. This is not strictly necessary, and even kind of a bad idea, right? Because it's potentially introducing restrictions, and in this case, this is very simple. This is very unlikely, but especially in more complicated functions and structures, adding this kind of stuff can often bite you in terms of introducing restrictions and things that you don't necessarily want. And if I leave it like this, Julia, already knows what these type parameters are. The compiler has access to them whenever it has access to the actual type. But unless I actually need to do something with those parameters, like if I need to do something like this where I promote the type or something like that, or convert or whatever, you really shouldn't include the type parameters in these function definitions, because no matter what, Julia will generate a different method for this function for every type of rational numbers that it sees. I don't need to inform it that it's a parametric function, unlike in C++, where I have to include that type parameter in my template every single time. Or at least, write the template up there and all that stuff. So now as far as what I've got here, okay, so let's set here. And make sure we're cool. Okay, so we're still trying to do a conversion operation here. So let's see what's going on. Let me just make sure I actually saved this. I don't know that I actually did. Okay, so we're still trying to convert to... oh, of course, I've forgotten exactly what I need right here. And this is the tricky part that I forget all the time, right? So the problem is here, I've defined 0 and 1, strictly speaking, for when I actually pass a value of rational number, right? Whereas what they've put in the test here, or the behavior we're actually expecting, is to pass a rational number type. And so let me show you what I mean by that. Let me just comment this out for a second, and I'll write a very similar version of this, right? Where I'll say x is, let's write just like this, right? Right, I pass in a value. What does it tell me, the 0 value is? If I run my tests here, everything passes, right? Because I've defined this. I haven't defined what's actually asked for here, which is a very slightly different version of this function that actually acts on the type and not a value of that type. And Julia is pretty different than a lot of languages, but not all languages by any stretch of the term, but especially languages that are involved in scientific computing, and that you can, types are first class, right? They're just data like any other. It's a homoiconic language, right? Types and code even are just things to be manipulated. So what I can do here is write, basically the same thing, where I have, right? So in the case of this 0 function, it's going to look basically the same, except I actually want this to be type rational number t, where t is an integer. my function n there. And I can return the same thing here. Same thing with my 1. And now I have basically both versions of these functions. Right? So this one is for types. This is for variables of a given type, if you want to think about it like that. And of course, I could probably be clever about making these, depend on each other in a clever way and all that, but I'm just going to write like this. And the reason why we were having trouble before is because Julia was seeing the fact that these were going to be integers, right? This type parameter, and it was trying to, fall back on rules that had already been defined based on those type parameters, and was having trouble doing what would be the necessary conversions, right? So this is a tricky problem, a tricky part of this type system. I'm actually glad that came up in this exercise, right? As you can see, it takes some time to think about. But once you run into this once or twice, it's easier to reason through, right? So we have this function is different from this function because this function acts on types and this function acts on variables that aren't types, that are of type rational number brace t. So back to my tests here. Well, looks like I have a whole bunch of arithmetic first. So what I'll do is, this is a big test set. At this rate, I probably won't get through all this anyways, so I will go ahead and, uncomment at least part of this. I did the end at the bottom there so I could get the whole block. Right, so addition is probably actually the harder of the operations that we'll have to do, right? Because you think about adding fractions, right, involves the common denominator. So, how are we going to deal with that? And the way to think about it is like this. So I will start by saying, well, first, we don't even have addition operation defined, so that's what I'm going to want to do. And I want it to be for rational numbers. And a good practice is, related to what I was just talking about not needing these type parameters, is to leave them off unless you'll need them, right? If I wasn't specifically defining something like an addition operation, I wouldn't necessarily even include the : rational number part, right? If I was just doing some kind of function that, I wanted to do some kind of operation on a rational number, and maybe other stuff too that, once I set up my rational numbers correctly would work the same, then I leave that off, and Julia can still reason about that. Just because I don't include these something like, integer here or whatever, doesn't mean that I haven't written a function that can be compiled, to many, many, many different methods depending on the input types. As long as the types themselves are defined, with these parameters and stuff accordingly. So the first thing I'm going to think about is, well, I'm going to need the numerator and the denominator of both of these rational numbers. So I'm just going to define a helper function to do that. Right up here with my numerator and denominator, I'll just define a function called numden. And what does that do? That just returns x dot num comma x dot den. Returns a tuple of these two values. I'll even just try it right now, right? I have this x, or here I'll do like this. I don't know why I keep capitalizing the u, but and I do right, and I get this tuple. If I check the type of that answer, it's a tuple of two integers. So Julia is a language that does make a distinction between tuples and vectors, right? So 1, 1 and bracket 1, 1 are two different things. This is a tuple, always immutable. This is a vector that I can change the values of, right? And this is just for convenience sake, right? This is, basically what's called destructuring and as a general term, to just split this into its constituent pieces. And the reason why I want to do that is because I'll write, a comma b is equal to numden x, c comma d is equal to numden y, right? Because I'm going to think about the formula like this, and I'll kind of write it in some comments here. right? So what we really want is to figure out what A over B plus C over D is equal to, right? And how do we do this when we're writing this out? Well, we figure out the what's called the least common multiple of the denominators, right? We say, okay, well, what's the smallest number that is a common multiple, right, of both of these numbers? And that is fittingly a built-in in Julia, right? I can just write G is equal to the least common multiple of B and D. And actually, I'll call it L for least common multiple. And that's what my new denominator is going to be, at least before I reduce. And then if we think about how this actually works, right, there's going to be two numbers, right? I'll call it L sub B times B, L sub D times D, right? Since this is the least common multiple of B and D, that means that there's two numbers that a number I can multiply B by and a number I can multiply D by to get this number. And that's ultimately what I want to multiply my denominator by to get the LCM in the first place, right? So in the case of like 2 and 3, right? So for B equals 2, D equals 3, the least common multiple is equal to 6, right? So I multiply B by 3, D by 2, get to 6. In this case, they're the same, but that's a special case. This is how it'll always work. And the reason why I'm writing it like this is because I want to multiply both numerator and denominator of my first fraction, my first rational number, by LB, both numerator and denominator of my second rational number by LD. And then I'll have the same denominator. I can add my numerators, and then I'll have my rational number. So I'll just use this notation, right? LB is going to be L over B. I'll just cheat real quick and do it like this. Cool. And then I'll say my new numerator, right? So I'll say numerator is equal to A times LB. My denominator is equal to C times, L underscore. I want to be careful there. And then return a rational number consisting of this numerator and denominator. Oops. And of course, I have to add these numerator and denominator together. I'm sorry about that. That's a flub on my part. The numerator is actually A times LB plus C times LD. Those of you following along were probably tearing your hair out just now. My denominator is actually just going to be L, right? I'll write that like this for the sake of illustration. Of course, I probably wouldn't want to do this. Although Julia's compiler is surprisingly smart about what's called, constant propagation, and realizing that variables are shadowing each other and that kind of thing. It may or may not catch that in this case. Right? So I'll write it like this. And so what have we got here? Okay. So already a bit of a problem in that somewhere we're getting a float, right? Julia also has what I think are more sensible names for all of the floating point types, right? There's no float and double. There's float 32 and float 16, right? That kind of stuff. So this is bad, right? And that's happening right here. Because Julia has, what is usually the helpful behavior of when I write 1 over 2, I don't get 0, I get 0.5. Even though 1 and 2, right, type of just 1 is an int64, so is 2, right? When I write those literals, I get integers. I'm doing an integer division, right? But I get the sensible mathematical result. And that's a slight problem here, right? Because that means right here, I'm getting, a floating point number. Even if I do something like, 3 over 3. So this is something to watch out for. This is a behavior that hews a bit closer to the way we think about things mathematically, but is a pretty big departure from especially a language like C or C++, right? Where if I were to write, would basically be the equivalent of writing int floor 1 over 2 in Julia, where I just get 0. So what will I do here? Well, now is a time where I will want these type parameters, right? Because I'm going to want to convert LB and LD to numbers of the suitable type, right? So I'll go ahead and add some parameters. I'll do TX and TY. I don't want to assume these are the same, right? I really have no reason to think that they would be. I'll again restrict these to be integers. And what will I do? Well, I will get this LCM, right? That's still going to be an integer. That makes sense, right? Because again, mathematically speaking, the least common multiple of an integer should always be an integer. But as far as these divisions, right, what can we do here? Well, I'll figure out what type these should get promoted to. And I will go ahead and convert both. Okay, so a better error this time, right? We've got rational number 0, 2 equals rational number 0, oh crap, right? This is basically the symptom of what some of you might have already noted yourselves, is that I haven't encoded or implemented any notion of reducing a rational number to its simplest terms. It's factoring out all of the common factors, if you want to think about it like that. And that's another property that would probably make sense to be something that I do before I even finish constructing the rational number, right? So I put it up in my inner constructor. And I say, okay, well, before I go ahead and do this last line, which I'm not going to comment out, right? Before I go ahead and do this last line, I'll do something like this where I'll say, what is the GCD, right? The greatest common divisor of N and D. And then I'll do the same thing. I'll say NG is going to be N over G, which I will make sure to convert back to the right type. Same thing with D. Right, I'm taking whatever the biggest common factor, the greatest common divisor these two both have. I'm dividing through by that greatest common divisor. Of course, I'll have to restart my REPL here. Run my tests. Boom, right? My addition test pass. So let's move on to subtraction. Okay. Well, now I can do a couple of different things, right? Strictly speaking, I could just take this function I just wrote and do one of two things. I could just, copy and paste and replace the pluses with minuses. Julia actually has some pretty neat metaprogramming functionality that would let me actually generate two different functions with the two different values without basically only having to write the one function once. I'm not going to get into any of that stuff because that's the part of Julia that, while very interesting, tends to be not all that useful, at least outside of the developing Julia itself community. So what I can do here is think about this mathematically, right? If I think about these as actual numbers, right, when we write A minus B, what we always mean, if we're talking about, a group or a field, or, I guess a group would be the most general version, right? When we write A minus B, we're thinking A plus negative B, right? So usually with plus, we're talking about commutative groups, so it doesn't really matter. We're saying this shorthand operation is really, it's taking A and adding to it the additive inverse, or, the inverse of B. So what I'll do is go ahead and think about it like that. I'll say base dot minus subtraction, but only for a single rational number, right? A unary minus. What's that? Well, that's going to be, I'll write it like this. nd is equal to numden x, return rational number, negative n d. So I don't want to do that. Of course, I'm running my tests here. I haven't done anything new yet. But now what I'll do is I have this unary minus. I'll write a binary minus. I'll define this binary operator exactly as I've written it down here. And I'll write x plus negative y. Again, don't really need the return, but I like to include it. And, operator precedence and all that stuff means that I probably don't strictly need these parentheses, but I'm going to go ahead and keep them there. And now my subtraction works as well. Excuse me. Multiplication up next. It's actually the easiest one of all, right? When you think back to learning fractions, multiplication was always the one I liked the best because we just multiply the numerator and denominator. And because our type automatically now reduces itself, we don't even have to worry about that part. Right? We could just write a comma b is equal to numden x, c comma d is equal to numden y, and I return rational number of a times c over b times d. Right? Multiply numerator and denominator. And again, you might say, oh crap, I have to worry about reducing these and Gray's comment. I've already done that. I cannot construct a rational number now without doing this reduction. So this is actually a part of Julia's type system that I really, really like, is the fact that we have this, end, I like to call it, it's called an inner constructor. I like to think about it as like an intrinsic constructor. Oh, that's not a great term. Or, colloquially speaking, like the last stop constructor, right? This is the end of the line as far as a construction operation goes. Every constructor will end up calling this one eventually, right? And that means every time I construct a rational number, I will be checking if the denominator is 0. I will be reducing the numerator denominator to lowest terms before I even construct the object. So now I don't have to worry about any of that stuff in these other operations. Kind of like how I could have defined subtraction exactly as I defined addition, just with the pluses swapped for minuses, right? But I decided, hey, I've done all this work already. I do have a good idea of how this works out mathematically, so I'll go ahead and encode that and incorporate that into my implementation as well. And the surprising part is, in most cases, that is, as long as you're careful about the type parameters and stuff and making sure that stuff is set up well, even a comparatively naive-looking implementation like this can perform just fine, right? A classic case as well, which, forgive the quick diversion, right? In many other languages, if I had two vectors, 1, 2, 3, y equals, 3, 4. Actually, let's do something even better, right? Like rand 100 or something like rand 1000, right? I have two vectors of 1,000 elements, right? And I wanted to think about multiplying them together, right? Contrived, but bear with me, right? In MATLAB or Python or whatever, right, I would have to think about this as vectorizing these operations, right? I have to write something like x dot star y. I could totally write this in Julia. This is totally legit. Right? It is not doing vectorization, though, or at least not in the same way that Python and MATLAB and others do, right? It's really just turning it into this, for I in each index xy. So I'll write like c equals 0s 1,000 xi ci is equal to xi times yi. Right? You would usually avoid doing something like this in Python or in MATLAB if you could get away with it, right? And that's because those are strictly interpreted languages, or at least Python is, right? MATLAB is a little bit in between there. And that every time as Python loops through each of these vectors, every time it hits a new entry, it has to, unless it's a NumPy vector or something like that, right? It has to say, hey, wait a second, what type is this? Hey, wait a second, what type is this? Whereas in Julia, as long as you haven't done something silly like a vector of any's or something like that, as long as it's something like this, it says, hey, no, I know that these are floating points or whatever. I could go ahead and do this operation, basically write this as assembly code and go from there. And even if I wrote what I wrote up there, which is this MATLAB style notation is totally good in Julia, right, on purpose. These compile to the same thing, right? So Julia is designed in such a way that a lot of times, if you stick close to mathematical notation, if you write things in a way that kind of you can think about naturally, that will actually get you pretty good performance and actually the best performance, right? The best way, to write the operation I just wrote, if I didn't have this already defined, would be to write it as a loop, which is very different than other languages. Okay, so I've got my multiplication with my last little bit of time, at least. Let's work on exponentiation. All right, so exponentiation as far as rational numbers go. Oh, let me make sure I've got. I'm just making sure I've got everything here. Begin. Okay, yeah, commented an extra end out there somewhere, but it's okay. Right. Let's see what we get. We actually already have exponentiation. Julia knows, hey, if we're talking about a subtype of number, which, integers are subtype of numbers, so since, or real is subtype of number, if we've got a subtype of number and we've defined a multiplication operation for it, unless we tell Julia otherwise, it will say, hey, I know what exponentiation is as long as it's an integer, right? So it's already given us this operation. And it's given us a well-optimized version of this operation because we've done the legwork up front. This is the part we will have to step in, though, right? Because we haven't really said what the hell it means to go from, integer and exponentiate to one of our rational numbers. I keep wanting to say complex number. So that's something we will have to step in for, right? And just to double check if I run tests, right, I get problems because it's trying to do this other stuff, right? Promotion. When you see stuff like this means that basically you're missing something as far as either an operation goes or a conversion goes. So usually I like to look for the operations first and then try the conversions later and all that stuff. In this case, it just means, it's trying to figure out what we mean by this, but it can't get there. So we go ahead and say, okay, well, this operation of function base dot caret. In this case, we're doing an integer or a real number even to a rational number, right? So we'll say x is real, y is rational. And again, even though I've written this abstract type here of real, Julia will still be able to generate optimized function methods for each different type of real. Unlike if I were to write real up here in this structure definition. And those are, two sides of the same coin. Because I've been careful with how I've set up the types here, at least parametrically, in my structure definition, Julia can then go from there and generate different methods for each subtype of real and each subtype or, instantiation of this rational type that we see. And this is one, right, where I have a notion of what this means, right? X to the power of, all right, nd is equal to numden y, x to the power n over d. And in this case, I don't want to intervene with this and, convert or anything like that. I do want this to be a floating point number. These will just be integers, so dividing them will give me a floating point number. And if I go ahead and run my tests, promotion of my types here, right? So let's see, 2 to my power rational number. So we are trying to convert here. And what is going on? Let's make sure I'm thinking about this correctly. And I think I'm actually pretty much out of time as it is. So let's see. My last little bit of time here. Power n over d. Let's make sure I'm thinking about this right. I keep switching to my other window here. y rational x to the power n over d. Just start over here. Okay, so what is happening here, right, is we're having trouble with promoting an integer and a rational number related to that integer. Right. So the last thing I'll do here is kind of talk about how we might resolve this, and that is to, tell the compiler how to do this promotion, to say function promote rule. So I've got to do this as a promote rule, because otherwise, if I override, I use this promote type function up here. If I were to start overriding this, or not overriding, but if I were to start writing new methods for this promote type function, that would be fine, except I'd have to think about all the different permutations of the inputs, which for 2 isn't so bad, but gets bad fast. I'd have to make sure about the order. I have to do all this kind of stuff. Whereas if I work with this promote rule instead and work on the types, so I'd have, type t, type, all right, ti for integer, type rational number tr, where ti is an integer, tr is an integer, right? Well, I want this to be promoted to a rational number. And, well, how this is going to come out, we'll have to do promote rule pi tr. Oops. And, I forgot my colon. Okay, so we're still running into trouble. Oh, it should be promote rule. Type. Oops, and this should not be, this should just be types. And actually, I'm sillier. Okay, do we want promote rule? Okay. So I've already gone a little bit over time. I won't spend any more time, at least on the stream, trying to fix this. This is one of those things that I'm sure as soon as I shut this off, it'll come to me. So maybe this will be the first thing I address next time. Maybe we'll start with some other stuff. Thanks everyone for joining me tonight. I really appreciate you taking the time to hang out and learn a little bit about Julia with me. Again, my name is Aaron. I'll be doing 2 more of these live streams this month of April, once a week on Thursday at 7 p.m. Eastern. So catch me here again next week and the week after. Thanks again, and everyone have a good night.